So learning about probability.
So,
Here we go. Hand me the remote.
What?
Right.
I think your camera's on.
You're on the Okay, here we go.
That's gonna be on here.
That is going to be a little awkward. All right, the last bit. Here we go. The last bit, the last section of the probability that we have to go through is conditional probability. We've done a little bit of this. This first part, with and without replacement. Here we go. The with and without replacement, we've done some. We've done mostly without. We've done one or two problems with. Excuse me. We've done mostly with, and we've done one or two problems without replacement. What's the difference? What is the difference? By the way, would you want this sent to you or put on Google Classroom? Would that help?
What is going on?
All right. While I'm putting this on your Google Classroom so that you can download and do whatever you want. Answer those questions. What is the difference between with replacement, without replacement? Why does it matter and what does it affect?
look at that. I was already ahead of myself.
If you want this, I was ahead of myself and already placed this on your Google Classroom, so you're more than welcome to get it.
Oh yeah, it's terrible sign.
Yes. Very nice. So yeah, you should have got a notification. Very, very good like that. All right, so if you want to print this, by all means, you can print it, go get it, write on it, do whatever, or you can download it as a document. You can just put everything right in there. Yes.
I'm going
I forgot I got to change.
What color is that?
this man.
So what's this? They can't take this.
Okay. Ryan, you should be good. Okay, so what is the difference? What is the difference here? Don't even go that deep into it. What is the difference between with replacement and without replacement? Yeah, it changes the total number of items that you can possibly come from. So it changes the possible outcomes. Can it change the desired outcomes?
No.
Yeah, but it can. Yes.
It
How
depends
can
if
it?
you pick.
Yes.
If you pick the one that's not going to be replaced.
Yes. So it can change both the desired and the total outcomes, number of possible outcomes or the desired outcomes. So be careful with what you're dealing with and what is being replaced or what is not being replaced. Okay? Because that's what matters. Those total numbers matter. If you don't change the numbers and it was without replacement, then your probabilities are going to be all messed up. Okay? So these three questions, even though they're different, they're very, very, very much the same. So, okay. Now,
What is without replacement?
Yes.
Without replacement means that you are not putting it back.
And yes, if you do look for this, this is on the internet in case you're looking for that. All right, so now, let's take a look at this. Oh, you got a bag of sweets, okay? So, Steve's got a bag of sweets. There's seven red sweets, 8 green sweets in the bag. Without looking, reaches in and picks out 2 sweets, one at a time. All right? No probabilities. Right now, think about what are the possible outcomes. What can happen in this situation? If this was a problem that was given you, what can happen? Just give me time to think. I'll come right back to you. Only want you to think about this one right now. Don't worry about calculating probability. Yeah.
2 greens, 2 reds, 1 red.
Okay, Brian, what do you think?
Two greens, 2 reds, 1 red.
Okay, 2 greens, 2 reds, 1 green, 1 red. Okay, so it says 2 green, 2 red, 1 green, 1 red. Okay, anything else?
What's the 16?
2 greens, 2 reds, 1 green, 1 red. Oh, not 16, sorry. Any others? What was that? Why could it be 1 red, 1 green? Are these 2 the same?
Yeah.
No.
Because one is picked out first.
Yes, because we have 2 separate pickings. Okay, now, calculate these probabilities.
The first one is 2 out of 15.
2 out of 15, okay?
The second one is 2 out of 15.
2 out of 15. I don't know, you just said it.
It's like all green, right? So it should be 2 out of 7. Or not 2 out of 8.
No, but then we're counting on the total number of greens. That's what.
Maybe we should calculate this together. He reaches in. First question, is he getting 2 sweets at the same time?
No.
No, it's 1 and then the next. So what do you know about those 2 reaches? They are what?
Without
So it's 2 out of
or with replacement. No, without.
Hang on to that one. What do we know? They're independent. What do we do with independent probability? We multiply. So we have 2 different choices. Well, for 2 greens, reach in first. What happens? He's choosing 1 out of how many?
15.
How many are in the bag? Is it 1 out of 15?
1 5.
No.
Not 1 out of 15. Why?
Yeah.
Because we're looking for green. How many green are there? 8. There are 8 green out of a total of 15. Now what?
7. It's 14.
Why 7 out of 14?
Because now there's only 14.
How do you know that?
Because
Because you took one out already.
We took one out, but were we told what we did with that?
You just said we took them out.
We picked it out. We don't, only given this information, we don't know whether he put it back in or whether he kept it out. Maybe the red ones are cinnamon. Maybe he doesn't like cinnamon. Do you like cinnamon?
Mhm.
Maybe the green ones are peppermint. Maybe he's like, I want to get. We don't know. We don't know whether he gave it away, ate it, put it back in, did whatever. So there are a bunch of different possibilities here because there are ones where he does eat it. So it would this be with or without replacement?
That would be without.
Without replacement. So we need to calculate the probabilities without, and we need to calculate the probabilities with. Okay? Because now we don't know which situation this is. So we could do 2 greens. Well, how do we get 2 reds? Yes, ma'am.
I really don't understand what you mean by what's replacement without it. Maybe it's for
Hand me that basket, please. Grab a marker. Without replacement. Oh, it doesn't go back in.
Yeah.
Now put it back in and grab another.
Oh. English.
Still without replacement. Okay, put it back. How would you grab 2? You didn't put either one of them back, that's without replacement. Now, put it back in. This time, once you pull it out, look at it, tell me what color it is, put it back in, and then grab a second one.
Green.
Put it back in, good. That's with replacement.
Those are replacing the first year.
So when you replace it, literally, it's putting it back into the mix.
Without replacement.
Without replacement is taking it, and now this sample is reduced by however many is going So this bag of sweets is very much like my basket of markers. Okay, I've got green, blue, brown, orange, and 2 black. Okay, so this problem is very much like this. If I told you to reach in and grab a marker, okay, maybe you put it back, maybe you don't, maybe you're a thief, maybe you take it. Okay, that's without replacement. Or maybe you're an honest person, here, you need it, borrow it, and then put it back at the end. That's with replacement. That's the difference. Okay, that's the difference. Now, the good thing is, in an IB situation, they will tell us which way we're looking at. They won't say with replacement, without replacement.
Oh, they'll say like,
Sometimes,
he puts
but
it in.
yes, they'll say, oh, he reaches in, eats it, and then does something else. He grabs a second one. Well, he eats it,
Then you can't.
he can't replace it. So if I eat the sweet, then it's without replacement. If I give it away, it's without replacement.
One year, returning to the place.
We don't know. So that's why we're calculating
Takes
both.
out 2 sweets.
He just takes out one and then takes out another one. We don't know whether he puts the first one back, whether he eats the first one, gives it away, we don't know. So that's why when we're looking at this, we calculate it 2 different ways. Only here. When you come up on an assessment problem, it will be clear whether it's going to be without replacement or with replacement. We're just covering both of these right now. Okay. So that's the gist of all this right here. Okay. These 2, I intentionally worded them to be very vague. Okay. Because when we're dealing with sweets, most of you have it in your head. Oh, no point in pulling it out unless I'm going to eat it. Okay. But that's not always the case. Maybe I reach in. I got a green. I don't want a green. I want blue. Okay. That was with replacement. Right? So maybe that situation happened with it. Maybe he reached in, maybe he didn't realize he only had red and blue left. Maybe he had red, blue, and, red and green. Maybe he had red and green, and he had a blue. He really liked the blues, but he already ate all the blues. Reached in, grabbed the red, put it back, reached in, grabbed the green, put it back, he looked in his bag. ate all the buildings. We don't know that situation. Okay, so that's why these two are intentionally written very vague like that, is to start thinking about whether it's with replacement or without replacement. Now, this one is more important. What situation is this?
Without,
Why without?
eats, because he eats it.
I can't put it back if we eat it. So what is the probability that he eats 2 green sweets?
The one that you put up there.
Okay, so it's without replacement. And we've got 8 out of 15 originally that are green. Then I ate that one. Okay, and then I chose, and when I choose again, or he chooses, not me, there are only 7 green ones out of 14, so we can reduce this. Take it out, make it easier on ourselves. 8 out of 15 times 4 over 2. 2 goes into 8, 4 equals 4 out of 15. Yes? Are we good?
Yes.
Now, the great thing about this is I don't need to do all this. I have my calculator. How do you multiply 2 fractions? Top, bottom, bottom. Numerator times numerator, denominator times denominator. Okay? Straight across. They are independent. They're not reaching and getting to at the same time. Okay? So it's one and then another. Now, the difficult thing is that we could have that situation. We're not going to worry about that right now. It's going to be 2 independent graphs. Fair enough?
Yeah.
All right. All right. What's the probability he eats 2 sweets that are different colors? Well, how many situations are there that he eats 2 different colors? This is a situation because is it different if he eats a red and then a green, or a green and then a red? Are those different probabilities?
Without replacement.
Without replacement,
But
there
with
is.
replacement, it
Wouldn't matter so much because it's the same out of everything. But without replacement, it changes because not only the numerator changes, the denominator changes, which means that our end probability is going to change. And with the replacement. Okay, so what is the probability he eats 2 sweets that are different colors? This is what we have, right? He eats a green and then a red, or a red and then a green. Well, what's the probability that he eats a green and then a red? How many greens are there?
8.
Starting with, reaches in and gets a green. How many are there? 8 out of 15. Well, then we reach in and get a red. How many reds are there? 7 out of 14. Okay, so that's one situation. Yes.
Why?
Because there were 15 to start. I ate 1. There are only 14 now. Well, now, this is a green and then red. Well, now, what about red and then green? What's the probability that I reach in and get a red first? 7 out of 15.
8 out of 14.
And then multiply that by 8 out of 14. Okay, so you can see there's slightly different probabilities. Now, I got this one and this one. What do I do with these probabilities? Why do I have them?
Because you're going.
If we look at the branch, because yes, that's exactly true. If we did this by a probability tree, okay? If we did this by a probability tree, what are the first 2 options? For my graph, what do I get? Red or green. Then my second graph from the red, what could I get? Red or green again. What about from green? Same, red or green. Now, if this is without replacement, this tree would look different than my with replacement. So what is the probability that we chose a red? Well, there are 7 out of 15. Well, then that means there are 8 out of 15 greens. Well, then if I ate 1, there would be, if I ate 1 red, There's no more, there's one less red, so that's 6 out of 14 now. Well, what's the probability for the green? Remember, it's gotta add up to be what? 1, so this has gotta be 8 out of 14. Okay, well, I chose green first. 8. How many greens are left? How many total are left?
14.
How many reds? 7 out of 14. Now, we want green and then a red, green and then a red, 8 out of 15 times 7 out of 14. Exactly what we had. That's one branch. Then we want a red and then a green, 7 out of 15 times 8 out of 14. A second branch. How do I find the total probability when I have? There we go. Down the branch, we do what? Multiply. When we have to put the branches together, we add. Okay? We add. Very good. What is this, by the way?
Both of them are 4.
Both of them are 4 out of 14. 4 out of 15. Simon, I don't know, these kind of shady characters. Oh, see? Well, let's see.
Wait, you add them first and then?
No, first is like separately, multiplying it for both, and then you add them together.
Well, let's do this. When I have 8 out of 15 times 7 out of 14. Remember, how do I multiply fractions?
You go straight.
Straight across. What's 8 times 7?
56.
56, yes. What's 15 times 14? 210. Okay, 210. What's 7 times 8? 15 times 14. 56 out of 210, 56 out of 210. What do we get? How much? 112 out of 210. 112 out of 210. And 15. All of hands right. Okay. Good deal? What do you have to do? What's the hardest part in these problems?
Decide if it's what the
So what's going to decide that?
reading the problem.
Reading. That's the hardest part about these problems. It's not doing the calculations. We've done so many probability trees already that you guys are pretty fairly certain. Boom, I can calculate these no problem once I see it in a tree. The problem is, you know what kind of tree it is. Is it a with replacement tree? Is it a without replacement tree?
Yes.
Okay? This one is what? 8. So it's what? Without. Okay, so be careful.
So if that's without, the width would be having the
The
same.
with replacement, all the denominators
Is 15.
would be 15.
That's-
Okay, but because we ate this, now it drops from total 15 down to 14.
Is that the only difference between the two?
Well, the numerator is going to change too, because if I eat the red,
Oh, yeah.
then the numerator is going to drop as well. If I eat the green, the numerator is going to drop as well. Okay? If I don't eat the red, or excuse me, if I eat the red, I didn't eat the green, so that number did not change. All good? All right. This is where we're going to start today. Yes, I know. So we already started. All right. The Bolshevik did not eat or give it away the first one. He puts them back. How does that change the problem? Well, we just answered that. How does that change the problem?
Makes it with replacement.
With replacement, which will make all the denominators in this situation 15. The numerators in the second draw, the second choice, are they going to be different than the ones in the first choice? No. All the probabilities are going to stay the same. Okay. Now, what's the probability that kid will not choose a red sweet? So this time it's with we're going back to the with replacement. Okay, so we're safe to assume this one, because we're talking about didn't need it, didn't give it away, just puts it back in the bag. So we're gonna change this.
It's the same as error 15.
So then we have 7 out of 15, 8 out of 15, 7 out of 15, 8 out of 15. What's the probability it does not choose a red sweep? Okay, so we could have green. Is there any other ones? No. So we do green. So 8 out of 15. 8 out of 15. What is the probability of 8 out of 15 times 8 out of 15?
64 over 20.
64 over 225. Can we reduce that?
16 out of 15.
16 out of 15? 16 out of 15. You sure about that?
I just moved to
Can't go from a number that's less than 1 to a number that's bigger than 1. Something's wrong there. Okay? Can't go wrong. Can't go there.
It's 64 out of 225.
He's too worried about the sweets. All right. So you can see how subtle little things will change the probabilities. A simple thing from keeping something else versus putting it back in. Right? Doesn't change the first choice, but it does change everything after that. Okay? So be careful. And the biggest kicker is not counting the probability, it's not having the numbers right, because you mixed it up. All right. I think this is pretty simple. Try this example. I'll be quiet for a little while.
What?
Yeah.
No problem. All right, ready these? Start with two. Yeah, please. At least there needs to be one. Okay, here we go. Should have had these done. 18 students in class, 8 boys, 10 girls. Teacher asked for 2 volunteers to hand out some books. Okay, we got how many things going on? We got 2 things, right? Volunteer 1, volunteer 2. All right. Probability both students are boys. Is this a with replacement, without replacement situation? Without. Why is it without? We're not eating anybody.
The volunteers, they're not going back in.
Because there are 2 volunteers. Okay? I need 2 volunteers. If I need 2 volunteers, one person can't do it both. I need a second volunteer. You cannot split yourself. Okay, so this is a without replacement. Right? So, in this case, both students are boys. By the way, what are we going to do with these? Multiply them. So we need to figure out the 2 probabilities. Both students are boys. Well, what's the first probability that the first volunteer is a boy?
8 out of 18.
8 out of
18.
18. Okay. Now, what's the second one?
7 out of 17.
7 out of 17, not 18. Because we not only took one of the boys, but one of the boys is also in the class. So we look at 1 out of each numerator and denominator. Well, both are boys. We're looking at 8 boys to start with. The first one, there are 8 different possibilities. But once we've chosen one of those volunteers to be a boy, how many are left? 7. And if we started with 18 and we've taken 1 away, how many are left out of the total? 17. Okay. So what is this probability? By the way, the probability of 32 over 153. We agree? Yes?
I got 28
28
out of
out of
153. Yeah, it's 28 out of 8 times 7 is 23.
8 times 7 is 23.
No, 28.
8 times 7 is about 28.
86.
Okay? So,
Are we going straight across?
yes. What's 17 times 18? Ladies and gentlemen, here we go. Oh, we need to focus.
306.
306. So now, what number goes into 56 and 306?
28 over 1.
They're both even, so we can divide both of these by 2. So that'd be 28 over 152. So be careful.
And you always have to simplify it.
IB wants you to simplify that. Until this past year, you're fine, but IB now wants you to simplify fractions.
Yes.
And yes, just put these in the calculator and then change from fraction to decimal. Just go math, F to D, fract to decimal, boom, enter. And it'll automatically give it to you in the lowest terms. Okay, or excuse me, decimal fraction. Now, neither student is a boy. That means both of them are what?
Girls.
Girls. So probability of 2 girls. Well, is this any different than the first situation? No. Except, how many girls are there? 10. So the first is 10 out of 18. And then,
9 out of
other way, yes. 9 out of 17. Now, ladies and gentlemen, show you a little trick, because some of you guys are getting hung up on your calculator stuff. How many times 9 go to 18?
twice. Oh, right.
What's 10 times 1?
10,
10. 2 times 17.
34. You get right by 2 and you get 2.
Both of them are even now. We can also, or we could have reduced it again and done 5. 5 times 1 is 5
You took 3 over
out of 17. Okay? Now, at least one student is a boy. How many situations are there?
Same.
Well, list the situations.
1 girl.
Okay, which way? Boy, girl, girl, boy, and boy. Okay? Do I have to calculate each one of these? Is this one any different than this one?
No.
Yeah.
Well, find out. Let's see. Probability that it's a boy.
8 out of 18.
8 out of 18 times
10 out of 18.
10 out of
17.
17. Remember, you took one away. Okay? Probability it's a girl, first one. 10 out of 18, and then 8 out of 7.
We're not equal the same.
Put your calculators in.
Oh,
How do you multiply two fractions? Straight across. Doesn't matter 8 times 10 or 10 times 8? Same result. 18 times 17, same thing as 18 times 17, yes? So, my question was, it doesn't make a difference here. No, so we just take this and do what to it? Well, we're trying to put it in, so we just double it. Because what do we have to do with each of these probabilities? Add them. So we find one of them, or both, and either one of them and double it, or just find both of them separate. Okay? My best suggestion to you is if you are confused, calculate each one of these and just simply add them together. It will take you no longer.
But isn't boy, girl, and girl the same thing?
We've just shown that in this situation, yes it is.
So we can
Okay? You can't just cancel them out because I don't want to talk about that because if I cancel them out, we're only going to calculate them once. Does that make sense? Because we have 2 volunteers. We have 2 volunteers. There is the same probability that it's a boy or girl. Okay? So, doesn't matter. Do we have to calculate all 3 of these, or is it just 2? So do I need this?
Well, if it's similar, no, you only do it once.
Why?
Because you've already said it's the same,
probability.
and so, because they have the same probability, you wouldn't add them, because then it's literally the same.
Then you get more than what you actually, because like having a boy and a girl is the same thing as having a girl and a boy, because you're obviously getting one boy and one girl in the same situation. So if you add them both together, then you're gonna have more than what you actually started with, or more than. It makes sense. It's like you're doubling it. Like
It makes sense.
Doubling your probability. In this case, do we want to double it? Because there are some times where it might come out to the same probability, but we do want to count both of these. Rolling dice. We have a blue die and a red die. Well, we get a 5 and a 5, or a 5 and a 4. A blue 5 and a blue 5 and a red 5 are 2 separate things, even though both of them have a 5. So it depends on the situation. Do we have this situation? Is this situation, are they 2 independent volunteers?
Yeah.
Yes. So do we want to calculate both of these?
And wouldn't it, like, if you wanted to calculate both of them, then it would say, calculate the probability that the first, like, who puts their head up first, you get it? So then you would have one girl, one boy, then one boy, one girl. But since we're not doing that, you're just calculating the probability with
2.
of 2 students, then you wouldn't have to.
Yes, that makes sense.
So can we guess?
Yes. You will see why I'm making a big deal about this in a minute. Okay? Because the next piece that we do is exactly that. It's going to say, calculate the probability that the second volunteer is a girl, given that the first one is a boy. Okay? So in this situation where we're only dealing with 2 things, not very important, but only because of the way it's worded. Once I change the wording on this, then that becomes a whole new ballgame, and then it does change the probability. Yes? Okay. All right.
Did you ask some questions?
You did. Because it's a generic, this situation is the same as that situation. So it's okay. One girl, boy is the same as boy, girl.
What else, boy?
Boy is 7. We already found that, so we did 28 out of 153. What do we do with that 28 out of 153? What would we do with these probabilities? Add it. So we take the 28 out of 153 and add it to, either, do we want to add it to 5 out of 17? No, we want to add it to whatever this guy is.
I do that too.
So, 428,
I want to point something out, and this is a very good question, because in this situation, there's no distinguishing between the two different volunteers. They don't have two different jobs. They have the same job. We're only talking about two things. Either one of them is a boy and one of them is a girl. They're both boys, or they're both girls. In this situation, it doesn't matter. Okay? Because of the way it's worded. If the teacher does this, well, since the first one is a boy, the next one has to be a girl. Or since the first one is a girl, the next one has to be a boy. That's a totally different situation. But since there is not that restriction on there, since that parameter is not put on here, this is okay to just calculate one of these. So we can scratch this one out because it's the only one that we need because of the way it's worded. And we do this one, boy, which is 8 out of 18, and then 7 out of 17. Okay?
You do that too?
Well, that's the other one that we did. So then we can add these two to get the probability.
Why did you cancel?
Oh.
Because,
I did.
sorry, listen. Okay? I need your complete undivided attention, right? Because this says that I just need 2 volunteers, and there are no restrictions on this. Getting boy-girl is no different than getting girl-boy. Okay? Because of the way that this is written. I can change that to put a condition on this. Once I put a condition on it, then it will make a difference girl-boy or boy-girl. This situation is not that situation. This one just says I have 2 volunteers, they're either boy or a girl. And there is no difference between volunteer 1 and volunteer 2, except for the sex of the volunteer. Okay? There's no other conditions on it. So, boy, girl is no different than girl, boy, which is why we do not need to calculate 3 probabilities. I only need 2. Because boy, girl is the same as girl, boy in this. Okay?
So what would be an example question where boy girls?
I need 2 volunteers.
One has to be a boy.
What's the probability that the second volunteer is a girl, given that the first is a boy? So that's going to distinguish between boy, girl, and girl, boy, because that's going to change this guy.
If that question arises, you have to make 2 tree diagrams?
No, it would be just 1, because it would be something like this. Okay, because it would be a without replacement kind of situation, where it's going to be boy, girl, boy, girl, boy, girl. All right, we're going to have that type of situation. This is my first choice, and this is my second choice. Okay, so it's just a difference in the wording. So we get
First one, 60.
80 out of 153 plus 56 out of 153 is equal to 136 out of 153. Okay? Boy, girl. Or girl, boy. And that boy, Yes. Great question, you guys all listening. If it said at least one girl, would it have changed anything? Yes, it would.
Yeah, the girl.
It would change the girl. Okay, so it would change its light. Okay, so be careful. Right? All right. Now, I'm gonna skip this next one. It's part of your homework. And now let's get into those questions that do matter which way it's written.
Actually, I'm going to do this.
Oh, okay.
All right, so you got a chart problem for your homework. Now we're gonna get into conditional probability. There's a word. There is a word that is going to give this situation away. Very simple word. And anytime you see this word, you are going to know that you are going to have this conditional probability. Yes, these are the ones that took off the quiz. What was that word? No, given.
Oh, yeah, give him that.
Yes, whenever you see the word. All right. Keyword in the conditional probability is the word given. When you see this, it changes all the rules because it uses a whole new formula. Right? The probability, or the way that we find this, and this is what this is written. Okay? Probability of A given B. That's what that says right there. Probability of A given B. So the probability of A given B is found by finding the probability of the intersection divided by the probability of B. When you are finding the probability of something, that probability is the bottom. Given is to the bottom. So probability of A given B. So the probability of that given goes on the bottom. Okay. Probability of what you're looking for is the intersection between the two events. Right? These, I will tell you now, if you don't pay attention, will mess you up. Okay, these are the hardest probabilities that we are going to face. These are the ones that tend to trip people up, and this is where a lot of students lose their marks in their IQ on the probability questions. Okay, yes.
Is this based on 3 variables or? No, but you give us a question that has.
You will not have a question with 3 variables. Now, if you're talking about 3 things, like a red, a blue, and a green, it can still work.
Color.
No, I'm going to say, what's the probability that a red ball is chosen given that a green ball is chosen? That would be. Okay. All right. So. Let's take a look at one of these given situations. This one should look kind of familiar.
Why yes? Well, not just because you're in school. This one should look very familiar, especially to those that have been paying attention.
Hey, that was on the homework. Yeah, so I just said.
Yes, this came from your homework, this first part, okay? So,
Wait, is this question the same?
nope. Same starter with different problems. Okay, so a school has 95 students who are taking IED diploma. All right, there are 45 students who study bio, 39 who study French, 24 study both bio and French. We did a Venn diagram for this. What did that Venn diagram look like? Start with the universal set. And we have two circles. Are they mutually exclusive or mutually inclusive? Inclusive.
So they're going.
So we've got bio, we've got French.
24 in the middle.
24 in the overlap.
And then you subtract.
The 21 biology,
Why 21 out here?
because you subtract the ones that take both biology and French away from the 20 people who take just biology.
Okay, so 45 study bio, but out of these 45, 24 also study French. So 45 minus 24 is 21.
Yes.
Okay? 39 study French, but out of those 39, 24 of them also study bio. So how many only study French? 15. How many people are we looking at? 95. 95 minus 15 is 70. Okay? 70 minus 45. 25 go out there. Okay? Because I just easily right here, you start 95, then this, then this. I just chose to start with this because I didn't find it.
But that's how you find the.
That's how we find out who's not in biology or French. Okay, now, given that a student is studying French, what is the probability that they are also studying bio?
Okay, so it's 24 over 15.
Given that they are studying French, what is that they're also studying bio?
24.
I'll give you a second. Just think about it up there, put it on your paper, and see what you get.
The intersection is 24. Right, and then you said that in the formula it could be intersection over.
Wait, was that what it was?
In this case, that's the already.
What's the P? What is that?
Do we get it?
Twenty-four over probably.
Oh, man. It's hard because in the beginning, it leaves you all the same.
What are you doing? Right. You say 25.
Alright, did we get an answer?
What's 24 times 95? Here, 24 times 95.
Oh, that's 80.
Times 9. What did you guys say? That is a large number.
I said 70, it should only be 80, sorry. Good catch. I was 10 off, sorry. 95 minus 15 is only 80, not 70. That doesn't change your probability for part A.
39
What did you guys say? How do you do it?
And that removes all of the. Are we ready? Well, how many guys tried to use the formula? Probability of A given B is equal to the probability of the intersection divided by the probability of B. How many guys try to use that? How many guys just try to use the Venn diagram? In this case, using just the Venn diagram is much easier. Okay, but we can still use it. Our two events, A and B, or P and Q, or in this case, B and F. Okay, so we are looking, in this case, what's the probability that they're, given that a student is studying French, that they study bio. So we're looking at the probability of bio given French. All right, so we have to find the probability of bio intersect French over the probability of French. So we could go to this. What is the probability of bio intersect French? 24 out of what? 24 out of 95. All over, what's the probability of French?
39.
39 out of 39 out of 95. Now I got a complex fraction. How do you simplify a complex fraction? So I got 24, I'm just moving this up here for more room. 24 out of 95 out of 39 out of 95. Now, this is where you need to pay attention. Something that you potentially have forgotten from the 6th grade. There's no such thing as a fraction bar. Fraction bar means what? Divide. Divide. 24 divided by 95 divided by 39 divided by 95. How do you divide two fractions? Multiply by the reciprocal. So 24 out of 95 times 95 out of 39. 95's cancel. How do you multiply two fractions? Straight across. 24 out of 39. Now, go to your Venn diagram. Given that a student is studying French, where is that? Given that the student studies French, it's only in the circle of F. Nothing else matters. It's only in this. Out of this, how many people also study bio? 24. How many are in this French circle? 24. 39. Don't worry about fractions needed. Sure, we would. I counted all of the French stuff.
Oh.
Because then this is including anybody that is taking French. Okay? So given that we are already in this circle, so that means I can ignore this and I can ignore that. I'm already in this circle. How many people in this circle also study bio? Well, it's only people over that. 24 out of everybody in that circle. Okay, so let's take a look at this one. What is the probability a student studying French but not studying bio?
15 over.
Oh, what's the given?
21.
Hold on, not numbers. What's the given?
Studying French. Not studying bio.
Not studying bio. How many people are not studying bio? Everybody outside of this circle. How many people are outside of this circle?
40, 50.
50. Out of that 50, how many people are studying French? 15 out of 15 out of 50. Okay. How do we get one? Well, we're given that it's not studying bio, so that means that it's everything outside of that circle. How many are outside of the circle? Which makes. Okay, so this is our given. That's the part that we're looking at. Well, out of that, how many people, out of this total, how many of those study French? How many are still in this part of the circle? 15. 15. Out of the total, 50. Okay. So in some cases, going by the diagram is actually easier than going by the formula. Sometimes it's not. Okay, if you're not a visual person, if you are somebody that says, oh, I gotta follow this formula, well, then follow the formula. Just be careful with your fractions. And you can do that in your calculator, just please make sure that you use parentheses. Your calculator will let you put in a complex fraction. Okay, so just be careful. All right? Should have written it there, now I gotta move it up. Oh, no, I did. All right, I thought I had another one. All right. Your turn. Try this.
I'm trying to read that word. It's literally just stuff. One degrees of
Yeah.
sound like somebody's driving.
What?
All right.
What? Oh, I heard about it yesterday. So in my life, that happened yesterday.
Come on, King, man.
I just love it.
As far as I'm concerned.
Oh.
So the tree would have pink and blue.
Okay, so who's brave enough to put the tree up there?
So,
Twelve.
Go for it, Well, come on, I hope you guys are goofing off. You got this. Hey, shh. If you don't have this done, I suggest you pay attention.
Don't fix it first, leave it.
Yeah, leave it. Be proud.
You bother me about it too.
Alright, so, do we agree with the tree?
Yes.
So we got pink and blue, those are our choices. 5 pink socks, 7 blues, we have 5 out of 12 for pink, 7 out of 12 for blue. Once we choose a pink, once she's chosen a pink out of the drawer, there's only 11 socks left. And there's only 4 more possibilities to get a pink, but there are still 7 possibilities to get a blue. But if she chooses the blue, there's still only 11 socks left. But to get a pink, there are still 5. If you get a blue, there are still 6. So the probabilities and everything in the tree are great. Good job. What is the probability that a nanny picks out 2 socks of the same color? How many branches do we have that give us the same color? 2. Excellent. Which one?
The pink and the pink and the blue.
Pink and the pink, the blue and the blue. So what do we do with those? All the way down, add. Yes. Perfect. Okay, so we are looking at those 2 branches. Okay, pink, pink, blue, blue. All right. So how do we calculate the probability of pink? Multiply. What do we get? You don't know. What are you supposed to be calculating? 20 out of 121. What about probability of blue? 42 out of 121. So, what is the probability that she gets the same color socks?
Just a second.
42 plus 20? 62 out of 121. Probability of same color. You straight?
Yeah.
Okay. Done. Given that she picks out 2 socks that are the same color, what's the probability that they are both blue?
42 out of 121.
Excellent question. How did you know? Yes, but why is it the 42 out of 21 and not the 62 out of 121 or the 20 out of 121? So, what do we have to ask? What's the question that we have to ask? Okay, is it a conditional? Is this a conditional? Is this a conditional probability?
Yes.
Yes. What is the given part of this condition? Same color. What's the probability that she has the same color sock? We We just calculated. 62 out of 121. That's what we got. Do you not agree with the 62?
The same color.
Okay, same color. Either she got two pinks or two blue, right?
Yes.
And then we added them together. So the probability of a same color pair of socks is 62 out of 121. Okay? Well, if we go back to the conditional probability, given this situation, given that we have the same color socks, now, this probability, 62 out of 121. Now, what is the probability that we have? Blue or blue? Yes, both blue.
Supposed to be on 42 over 121 over that.
42 out of 121 goes there.
Oh, because it's blue over.
Because we've chosen the blue out of the same color. So we're looking at the same colors, so we're either gonna look at the 20 out of 121 or the 42 out of 121, because those are our two options. But because it is both blue, we went to the blue brick. Yes.
I didn't know which one would be.
This B, this is the one that is,
So would it be like given blue out of both? Wait,
How much you do?
oh, it's, okay, I understand.
It's his intersection.
Oh, you saw that.
So it's the intersection between blue socks and both colored socks.
Isn't the denominator only on?
yes,
Isn't the denominator only focusing on one? Very
focusing on given situation. What's the given situation in this problem? That we have the same color socks. We just calculated this probability for this same color socks. Okay? Yes.
How did you get 121? Did you multiply it?
No. How many branches do we have?
More.
Well, how many branches then we have the same color? 2. When we have multiple branches, what do we do with the probability for the branches? Add them. So to get this, we took 20 out of 121 plus 42 out of 121. Same denominator. 12 times 11. Yes. You're the only person that picked that up. 121 is not 12 times 11. Very good. And even though you said that, and I've said that, how many people in this room right now have heard that? Half. You know why the other half haven't? They can't stop. Which is the same reason why when you have this homework, that other half can't do these problems. And I'm okay with that, because that's a self-consequence. In other words, when you guys don't pay attention, don't come to me. Okay? 12 times 11 is not 121. 11 times 11 is 121. 12 times 11 is 132. You know that. We're paying attention. Okay, come on. So, it's 20 out of 132. 132. Don't apologize, it's a good thing. You were actually paying attention and trying to keep up. You just made a mathematical error. That's fine. Yeah, right. We all. Yeah, right. Okay, now. Does that change the result? What's the given information? What is the thing that is given in this?
So she picks out two socks.
That we are dealing with the same color socks. And we just calculated that. So that's the given part. Now, out of that given part, what are we looking for?
The probability that they're both blue.
That they're both blue, which is why we go to the 42 out of 132. And the 62 out of 132. Well, 42 out of 132 divided by 62 out of 132, what do we get? Well, when I have a complex fraction, how do you get rid of the denominator within the denominator? Or the denominator within the numerator? Multiply the top and bottom by that denominator. This leaves 42 out of 62. But what number goes into 42 and 62? Okay, these two, they're both even. We got 21 out of 31. Okay. The hardest part about these problems, aside from simple mathematical theory, is reading. Slowing down and reading. I can guarantee you, if you do not slow down and read these problems, you will make a mistake. Okay? Please, take your time on these problems. Okay? They're not super difficult as far as the mathematics that you have to do. What's super difficult is what they're asking you to find. Those of you that are getting ready to sit for the SAT in about, what, 3 weeks?
Next week.
Okay, next week for 3 weeks, whatever.
I'm not sitting for it, I just missed.
December 5th, I think is the day.
Yeah.
Okay. Whether you're taking the subject test or whether you're taking the general knowledge test, same thing. That mathematics is not deep. Okay? The general knowledge only tests up through basic algebra 2, if that. So essentially, 9th and 10th grade mathematics. Okay? It does, however, test how you read mathematically. Your mathematical IQ as far as reading intelligence. The mathematics behind it is not deep. So if you're in that general knowledge test and you're doing some wicked calculations, stop. Because they're not that deep. Right? Stop. Redo it, rethink it. There is very basic trigonometry. Just right triangle trick. There is no non-right triangle trick. There's no sine, law of sines, or law of cosines on the general knowledge test. On the subject matter test, there might be some law of sine, law of cosine. There might even be some matrices, which, if you are taking the subject matter test, you better study up on because the IB does not do matrices. Therefore, we don't do matrices in the pre-IB classes. That's a content area that you're going to have to study up on 2x2 and 3x3 matrices. So I will tell you that. Let me see what else. Again, not a whole lot of deep trigonometry, but it is there. Some of the more involved trig stuff. But it's not super, super, super deep. So if you find yourself going 5 to 10 minutes into a problem, skip it. If you're taking too long in that problem, go to the next one. Same thing as these. It's not the deepness of the mathematics, it's what is being said. What am I being asked? Okay, so slow down and be very critical about what I'm being asked. All right? Your homework is to finish the problems that are long distance. Got that? Couldn't get to a math class without that. Come on.
You didn't make it. I made it for you. You take this up.
Gentle, give
Tomorrow?